Welcome to the tutorial on deep energy-based learning. My name is Jianmen Xie from Baidu Research. I got my PhD degree from University of California, Los Angeles. My current research interest lies in statistical modeling, computing, and learning. There has been growing interest and advance in deep energy-based learning. The energy-based model can unify the bottom-up representation and top-down generation into a single framework, which makes it different from the other generative models, such as generative adversarial network and variational auto-encoder. This tutorial will provide a quick introduction of current deep energy-based modeling and learning methodologies. I divide the material into 4 parts. I will start from the background of energy-based model in part 1. In the second part, I will present deep energy-based models in data space. In the third part, I will introduce the energy-based cooperative learning, which is a joint training framework of an energy-based model and a latent variable model. In the fourth part, I will talk about latent space energy-based model, where we learn an energy-based model on top of a generator. I will talk about the background from the perspective of computer vision. Here's the outline. An image is a collection of numbers indicating the intensity values of the pixels, and is a high-dimensional object. A population of images, such as images of cats, can be represented by a probability distribution, which is parameterized by a set of parameters that can be trained from the observed data. Such a probabilistic model is useful for supervised, unsupervised, and semi-supervised learning, as well as model-based reinforcement learning. Therefore, studying probabilistic model is a fundamental problem in computer vision and machine learning. The energy-based models that we will study in this tutorial is one type of probabilistic models. Consider the space of all the image patches of a fixed size, for example 10 by 10 pixels. We may consider an analogy between this image space and our three-dimensional universe. The distribution of the mass between our universe is highly uneven. There are high concentrations of mass between the stars, while the mass spreads over the nebulas with low densities. The distribution of the population of natural image patches in the image space is also highly uneven. In the image space, we need to identify, map out, and catalog those high-density clusters, such as stars, as well as the low-density regions, such as nebulas. A concept is a set of images which share some sufficient statistics, and the set can also derive a statistical model which is in the form of energy-based model. The energy-based model can also be called the Markov random field, Gibbs distribution, descriptive model, maximum entropy model, or exponential family model. That is to say, a concept can be represented by an energy-based model in the image space. In 1970, Grananda was a pioneer using statistical models for different visual patterns. In recent decades, Grananda contributed to computational statistics, image processing, pattern recognition, and artificial intelligence. He coined the term pattern theory to distinguish from pattern recognition. Grananda's general pattern theory is a mathematical formalism to describe knowledge of the world as patterns. The Brown University Pattern Theory Group was formed in 1972 by Grananda. Many mathematicians are currently working in this group. Noteworthy among them being the field's methodist, David Mumford. Mumford advocated Granada's pattern theory for computer vision and pattern recognition. There are some principles in pattern theory. First, patterns are represented by statistical generative models that are in the form of probability distributions. Secondly, such models can tell us what the patterns look like by sampling from the statistical models. Thirdly, the models can be learned from the observed training examples by analysis by synthesis scheme. Last but not least, pattern recognition can be accomplished by likelihood-based or Bayesian inference. In the field of computer vision, the frame model was proposed for texture modeling. The frame model is a Markov random field model or an energy-based model whose energy function is the sum of translation invariant potential functions that are one-dimensional nonlinear transformation of Gabor filter responses. It assumes a dictionary of Gabor filters is given, and only learn weight, theta, on top of the nonlinear transformation of filter responses. These are some synthesized texture patterns sampled from the learned frame model by Gibbs sampling. Since the original frame model for texture is homogeneous, it cannot be used for object patterns. The inhomogeneous frame model is a non-stationary Markov random field model that reproduces the observed statistics of Gabor filter response at all the different locations, scales, and orientations. It uses MCMC for sampling. In the language of neural network, the energy function of the inhomogeneous frame model are two-layer network, in which one convolutional layer is given and one fully connective layer is learned. The sparse frame model is a sparse version of inhomogeneous frame model, where only a small number of Gabor filters are included into the energy function. The selected Gabor filters form a template of sketches that is an interpretable representation of the object. Generative boosting and shared sparse coding are two approaches to specify the frame model. To improve the expressive power, the deep frame model replaced the Gabor filters by VGG feature and learn one fully connective layer. These are the generative examples by Langevin sampling from the learned deep frame model. Instead of using filters from pre-trained ConvNet, the filters can be learned from the observed data. The resulting model is the generative ConvNet model. Such a model can be considered a recursive multi-layer generalization of the original frame model. It is also a deep energy-based model. Let I be an image. The generative ConvNet model is a probability distribution defined on image domain. Q is a reference distribution, for example, a uniform or Gaussian distribution. Z is the normalizing constant. Fi is parameterized by a ConvNet structure that maps the input image to a scalar. Theta contains all parameters of the ConvNet. This tutorial will use the generative ConvNet as an example to introduce the deep energy-based modeling and learning. This is a list of references of Part 1. Now we will study the deep energy-based model in data space. Maximum likelihood estimation is a commonly used method to train energy-based models. Suppose we observe training examples xi, I from 1 to n, which follow the unknown data distribution p data. The objective function of maximum likelihood estimation is the average of the log probability density of the training examples. The gradient of the log likelihood involves an expectation term which is analytically intractable. The expectation term comes from the derivative of the log z, where z is the intractable normalizing constant. We saw the derivation of the gradient of the log likelihood on your right-hand side. The expectation term is intractable because x is high-dimensional. Consider x is a 100 by 100 grayscale image, and each pixel can take a value from a region of 0 to 255. The image space is too big to do summation over x for computing the expectation, according to the definition. Therefore, it has to be approximated by Markov chain Monte Carlo MCMC method, such as Langevin dynamics or HMC. To be specific, we can sample x tilde from the model distribution and use the sample average to approximate the expectation. Now we shall study Langevin dynamics, which is a gradient-based MCMC method that is important and useful to compute the gradient of the log likelihood. For high-dimensional data x, sampling from the distribution P of x, which is in the form of energy-based model, requires MCMC, such as Langevin dynamics. The Langevin dynamics is a stochastic gradient ascent algorithm that finds data x to maximize the function f. A larger f corresponds to a larger probability density. Delta t is the step size, and et is the Gaussian noise term for randomness. As the step size goes to 0 and the number of steps goes to infinity, the distribution of the generative examples will converge to the target distribution P of x. There are different implementations of the Langevin sampling. For the persistent chain, we run a finite step MCMC from the synthesized examples generated from the previous epoch. The contracted divergence runs a finite step MCMC from the observed examples. If VV runs a finite step MCMC from Gaussian white noise, this will lead to a non-persistent short-run MCMC. This is a full description of the MCMC-based MLE algorithm for training energy-based models. At each iteration, we first sample synthesized examples from the learned distribution by MCMC, and then use the training examples and the synthesized examples to compute the gradient of the log likelihood, such that the model parameters can be updated by a gradient-based learning algorithm. The learning algorithm tries to match the synthesized examples to the data in terms of statistics. Such a learning and sampling algorithm is called analysis by synthesis algorithm. The analysis by synthesis learning algorithm is a mode-seeking and mode-shifting process. Here is an illustration. The red curves and blue curves represent the negative energy landscapes of the true model and the learned model, respectively. The red crosses indicate observed data, and the blue circles indicate the synthesized data. Figure 1 is the mode searching by Langevin dynamics, which finds high-score modes in the landscape of the model and placing the synthesized examples around the found modes. After that, the algorithm shifts the high-score modes toward the observed examples, which is shown in Figure 2. Figure 3 is the mode chasing, which researches the high-score modes in the updated landscape of the model. Figure 4 is the mode matching, where the modes in the learned landscape eventually match the ones in the data distribution after a few iterations of mode searching and shifting. I want to show you the adversarial interpretation of the energy-based learning. The update of parameters theta is based on the gradient of the log likelihood, which is the difference between the observed statistics and the synthesized statistics. If we take out the gradient sign of the summation operator and define a value function v, which is a function of the synthesized example x tilde and the learning parameters theta, the gradient of the value function is equal to the gradient of the log likelihood. We can easily find that the learning and sampling algorithm actually play a minimax game. In the learning step, the algorithm finds theta to maximize the v, and in the sampling step, the algorithm finds x tilde to maximize the score function f, thus minimizing the value function v. Given an energy-based model P of x, z is the intractable normalizing constant, fx is the negative energy, theta is the parameters. The maximum likelihood learning of the energy-based model P of x requires the MCMC sampling, such as Langevin dynamics, to approximate the gradient of the log likelihood. The Langevin dynamics is an iterative algorithm, where each step consists of a gradient ascent that maximizes the function f and a noise term serving as Brownian motion. The model P of x can be highly modular, and gradient-based MCMC may get trapped in local modes, so that different Markov chains initialized from different starting points do not mix. We now consider the learning algorithm based on short-run MCMC. To use a short-run MCMC, we initialize the Langevin dynamics from a fixed initial probability, P0, and run a fixed number of k steps. The resulting marginal distribution of sample x after running k steps of MCMC starting from P of 0 is denoted by Q of x. Since the short-run MCMC is non-convergent, so Q of x is not equivalent to the target distribution P of x, and x is highly dependent to its initialization. Therefore, the k-step short-run MCMC can be considered as a latent variable model or a generator with initialization z as latent variable. Here, we use M to be the transition kernel of k-steps of MCMC toward the target distribution. The short-run MCMC can be written as x equal to M of z, where M is nonlinear mapping and z is latent variables, following the distribution P0. This figure shows some generative examples by the short-run MCMC. Training the parameters of the energy-based model with a non-convergent short-run MCMC is no longer a maximum likelihood estimator, but a moment matching estimator that solves this estimating equation, which is the perturbation of the MLE estimating equation, where we replace the model P by the short-run distribution Q of x. Now, I want to show you how to understand the learning behavior of the short-run MCMC. Let us consider a simple model where we only learn top layer weight parameters theta. The blue curve illustrates the model distributions corresponding to different values of parameters. The black curve illustrates all the distributions that match the data distribution in terms of the expectation of h of x. The h of x is a feature vector of x. The ideal MLE solution, that is the green dot, is the intersection between the blue curve and the black curve. The red dotted line shows that the MCMC starts from P0 and runs toward P with theta hat MME. MME means moment matching estimator. But the MCMC stops after k steps, reaching Q with theta hat MME, which is the learned short-run MCMC generator. Even if the learned P theta may be biased from MLE, the resulting short-run MCMC is considered a valid model, in that it matches the data distribution in terms of expectation of h of x. As we mentioned, the short-run MCMC can be considered a latent variable model or a generator. Therefore, it can be used for reconstruction or interpolation. In the top figure, we show that with the short-run MCMC generator, we can find latent variable z for each image and perform linear interpolation on the latent space. The transition in the top figure displays the sequence of generation with interpolated z. In the bottom figure, we show that the short-run generator can perform reconstruction by finding z to minimize the reconstruction error. Both of these experiments validate that the learned short-run MCMC is indeed a latent variable model. The deep energy-based models can be scaled up in a multi-degree modeling and sampling strategy. Between each learning iteration, for each observed training image, we generate synthesized images at multiple grids by initializing the finite step MCMC sampling from a minimal 1x1 version of the training image. The synthesized image at each subsequent grid is obtained by a finite step MCMC initialized from the synthesized image generated at the previous coarser grid. After obtaining the synthesized examples, the parameters of the energy-based models at multiple grids are updated separately and simultaneously based on the differences between synthesized and observed examples. The multi-grid or multi-resolution modeling and sampling can be used for image generation, image inpainting, and feature learning for classification. The multi-grid EBM can be learned from a single observed images to capture internal statistics at different resolutions and generate realistic images with arbitrary sizes and aspect ratios by sampling from the learned distribution that captures different scales of internal statistical properties of patches between the input image. The left figure shows the synthesized images. Each row is one example. The right figure shows the influence of the numbers of scales. The high-resolution energy-based model can be trained in a multi-stage cost-to-phi expanding and sampling scheme. We incrementally grow the EBM from a low resolution to a high resolution by gradually adding new layers to the energy function. Different from the multi-grid setting, in which we learn multiple EBMs at different resolutions simultaneously, the multi-stage setting only learns a single EBM at the highest resolution. The motivations of both multi-grid and multi-stage EBMs are to stabilize the learning and sampling of EBMs. But the multi-stage EBM might have less parameters, since it only keeps one energy function at the end. Here are some synthesized examples generated by the multi-stage EBMs. The left figure shows the MCMC generative sequences on CAA dataset. Each MCMC contains 50 Langevin steps. The right figure shows the synthesized images at the resolution of 512 by 512 pixels. Now, I want to talk about some generalizations of the generative common-net. The spatial-temporal generative common-net is an energy-based generative framework defined on video. It generalizes the generative common-net by using a bottom-up spatial-temporal common-net to parameterize the energy function, which is helpful to capture spatial-temporal information from videos. The model is in the form of exponential tilting of a Gaussian reference distribution and trained by analysis by synthesis. Langevin dynamics is used to draw samples from the distribution. Here are some examples of learning to synthesize dynamic textures by spatial-temporal generative common-net. For each example, a single model is learned from a single observed video, and 3 generative videos are displayed. Energy-based generative voxelnet is an energy-based framework for 3D volumetric shape representation. It parameterizes the energy function by a bottom-up 3D convolutional neural network structure and follows the same modeling and learning scheme of the generative component model. This model is powerful for 3D volumetric shape generation and outperforms GAN-based and VAE-based methods in terms of inception score, which is a measure to quantify the synthesis quality. Point cloud is another important data format to represent 3D objects. Compared with voxel representation, point clouds can provide a compact and detailed representation of a 3D object. Learning a generative model of 3D point clouds for point cloud generation is a fundamental problem for 3D computer vision. A major challenge in modeling 3D point cloud is that, unlike images, videos, and volumetric shapes, point clouds are not regular structures but unordered point sets, which makes extending existing energy-based paradigms intended for structured data not straightforward. Energy-based generative point net is an energy-based model for unordered point clouds, with the energy function parameterized by a well-designed input permutation invariant bottom-up network. The MLE training of the model follows analysis by synthesis. The input permutation invariant bottom-up network, F, first takes all unordered points as input, encodes each point into features by multi-layer perceptron, MLP, and then aggregated all point features to a global feature by average pooling, and eventually outputs a scalar by another MLP. Figure A shows some 3D point clouds generated by the learned energy-based model by short-run MCMC. Since the model is trained with k-step, short-run, and non-convergent MCMC, the sampled point cloud is highly dependent to its MCMC initialization. Therefore, the short-run MCMC process can be regarded as a k-layer flow-based generator or a latent variable model with the initial starting point as the continuous latent variables. We can use this latent variable model for reconstruction purpose. To be specific, given the new testing point cloud, we find the latent vectors of the short-run MCMC generator to minimize the reconstruction error. Figure B shows the visual performance of reconstruction. The second row displays the result of the energy-based generative point net, and the third row displays a baseline. Since the short-run MCMC is a latent variable model, we can perform interpolation in the latent space to demonstrate the learned latent space is meaningful. Figure C shows two examples. The transition in each row displays the sequence of reconstructed point clouds with the linear interpolated latent vectors. Now, I will talk about energy-based continuous inverse optimal control. The problem of continuous inverse optimal control is to learn the unknown cost function from expert demonstration. This problem can be studied in the framework of energy-based model, where the observed expert trajectories are assumed to be random samples from a probability density function, which is defined as the exponential of the negative cost function up to a normalization. In particular, I talk about the control problem of finite time horizon, where the trajectory is over a finite period of time. I will focus on the problem of autonomous driving as a concrete example. Let xt be the state at time t. The state might include longitude, latitude, speed, heading angle, acceleration, steering angle. Let ut be the continuous control or action at time t. The control might include the change of acceleration, change of steering angle. The dynamics f is known. Both x and both u represent time sequences of state and control respectively. The trajectory is the pair of both x and u. The cost function with learnable parameters is defined on the trajectory and some history and environment conditions. The problem of the inverse optimal control is to learn the parameters of the cost function from expert demonstration. The distribution of control conditioned on the history and environment can be represented by an energy-based model with the cost function serving as the energy function. State x can be determined by the control u according to the dynamic function. As to the demonstration, control u are assumed to be sampled from the distribution, so that u tends to have low cost. The parameters of the cost function are trained by maximum likelihood by analysis by synthesis. For the synthesis step, the trajectory of x and u can be sampled by Langevin dynamics or predicted by optimization method that directly minimize the cost function. Once the cost function is learned, the trajectory prediction can be performed by Langevin sampling from the conditional distribution. Here are some example results of trajectory prediction. The red dot represents the ground truth trajectory, and the green dot and the blue dot represent the results obtained by EBM and GALE, which is gun-based baseline. This is a list of references of Part 2. In Part 3, I will present the energy-based cooperative learning framework in which a deep energy-based model and a deep latent variable model cooperate with each other to learn the data distribution. I will start from introducing the deep latent variable model and its maximum likelihood estimation algorithm. A deep latent variable model is a top-down generator model that transforms a low-dimensional random vector into a high-dimensional data space by a deep neural network. Let X be a high-dimensional example, such as an image. Z be a low-dimensional latent vector that captures semantic meanings of the observed example and follows a simple prior distribution, such as Gaussian distribution. G is a deep neural network that contains all learning parameters. The generator defines a conditional distribution Q of x given z, which is a Gaussian distribution with the mean equals to the output of the generator. The log of the joint distribution corresponds to the reconstruction error of the decoder G of Z. The posterior distribution, which is the conditional distribution of Z given X, can be derived by the Bayes rule. The posterior distribution is intractable because the marginal distribution Q of X is intractable. The gradient of the log likelihood of the generator with respect to the parameters alpha is given by this formula. It is an expectation under the posterior distribution. In order to evaluate the learning gradient, Markov chain Monte Carlo, such as Langevin dynamics, is used to sample from the posterior distribution. For each observed example X, we infer its latent vector Z by the Langevin inference process, and then update the parameters alpha by maximizing the joint log likelihood of X and Z. The key steps for the Langevin inference and the parameter update are the computations of the gradient of the decoder G. In the Langevin inference, the gradient is with respect to Z, while in the parameter update, the gradient is with respect to the parameters alpha, both of which can be efficiently achieved by backpropagation in the current modern deep learning platform. Therefore, the MLE of the generator alternates the Langevin sampling for inference and the gradient descent for parameter update. Let's compare the deep energy-based model and the deep latent variable model. The deep energy-based model has a bottom-up level that maps the data into a scalar, which serves as an objective, value, or cost. The energy-based model is easy to specify and define an explicit density, but it's hard to draw samples. It is powerful to approximate the data distribution. On the other hand, the deep latent variable model or generator model has a top-down level that maps a latent vector to a high-dimensional example. It is a sampler or policy. It is easy to draw samples by direct ancestral sampling. It has an implicit marginal density and might not approximate data density as well as deep energy-based model. Both EBM and generator can be learned from the training examples by maximum likelihood. The likelihoods of both models involve intractable integrals, and the gradients of both log likelihoods involve intractable expectations that can be approximated by Markov chain Monte Carlo MCMC. The training algorithm for the EBM alternates between Langevin revision and density shifting. Intuitively, in Langevin revision step, the EBM is dreaming by synthesizing examples from the current model. In density shifting step, the EBM updates its parameters to make the dream more realistic. The training algorithm for the generator level alternates Langevin inference and reconstruction. It is similar to the EM algorithm, where the Langevin inference can be mapped to the E step, and the reconstruction step can be mapped to the M step. It is an unsupervised learning algorithm because the latent factors are unobserved. Intuitively, in Langevin inference step, the generator is thinking about each observed example by inferring the latent factors that can reconstruct it. The thinking involves explaining away reasoning. The latent factors compete with each other in the Langevin inference process to explain the example. In the reconstruction step, the generator level updates its parameters to make the thinking more accurate. Even though the two MLE algorithms can operate separately on their own, they benefit from cooperating with each other, where the generator plays the role of the student and the EBM plays the role of the teacher. A student writes up an initial draft of a paper. Her advisor then revises it. After that, they submit the revised paper for review. The student then learns from her advisor's revision, while the advisor learns from the outside review. In this analogy, the advisor guides the student, but the student does most of the work. The needs for cooperation stem from the fact that the Langevin sampling in EBM and Langevin inference in latent variable model can be time-consuming. If the two algorithms cooperate, they can jumpstart each other's Langevin sampling. The resulting algorithm seamlessly interweaves the steps in the two algorithms with minimal modifications. Intuitively, while the EBM needs to dream hard in Langevin revision for synthesis, the generator needs to think hard in Langevin inference for explaining away reasoning. On the other hand, the generator is actually a much better dreamer because it can generate images by direct ancestral sampling without MCMC, while the EBM doesn't need to think in order to learn. Specifically, we have the following steps in the cooperative learning algorithm. Please look at the diagram on your right-hand side. In step 1, we first generate latent factors from Gaussian distribution. In step 2, we then generate the initial synthesized examples using the generator. These initial examples can be obtained by direct ancestral sampling by a top-down process with the generative latent factors. In step 3, starting from the initial synthesized examples produced, we run Langevin revision dynamics for a finite number of steps to obtain the revised synthesized examples. In step 4, the generator can learn from the revised synthesized examples produced by the EBM. For each revised synthesized example, we know the values of the latent factors that generate the corresponding initial synthesized example. Therefore, we may simply infer the latent factors to be their known values given in initial generation, or initialize the Langevin inference dynamics from the known values. In step 5, we update the EBM by using the revised synthesized examples and the training examples. In step 6, we use the revised synthesized examples and the inferred latent factors obtained to update the generator. The generator learns from how the EBM's MCMC revised the initial draft by reconstructing the revised draft. This is called MCMC teaching. The reason we let the generator never learn from the revised synthesized examples instead of the observed examples is that the generator does not know the latent factors that generate the observed examples, and it has to think hard to infer them by explaining away reasoning. However, the generator knows the value of the latent factors that generate each initial synthesized example, and thus it essentially knows the latent factors when learning from the revised synthesized examples. By reconstructing the revised synthesized examples, the generator traces and accumulated the Langevin revision made by the EBM. This cooperation is beneficial to the generator by relieving it the burden of inferring the latent factors. The generator can provide a limited number of examples, and in each learning iteration, the generator supplies a completely new batch of independent examples on demand. The EBM only needs to revise the new batch of examples instead of generating a new batch by itself from scratch. This cooperation is beneficial to the EBM by relieving it the burden of synthesizing examples from scratch. Compared to the adversarial learning of the generator, the cooperative learning has an actual refinement process guided by the EBM. I use the following diagrams to further illustrate the basic idea of the MCMC teaching. Double line arrows indicate generation and reconstruction in the generator network. Dashed line arrows indicate Langevin dynamics for revision and inference in the two models. The diagram on the left illustrates a more rigorous method, where we initialize the inference of Z tilde from Z head, and then update the parameter alpha of generator based on Z tilde and X tilde. The diagram on the right shows how the two models jumpstart each other's MCMC without Langevin inference. In a cooperative learning algorithm, the part of learning of the EBM is modified contracted divergence, and the part of learning the generator is MCMC teaching. In the traditional contractive divergence, the Langevin dynamics starts from the observed training examples. In cooperative learning, the Langevin dynamics starts from the initial synthesized examples generated by the generator. Let M theta be the Markov transition kernel of multiple steps of Langevin dynamics that samples EBM p theta. For any distribution P and any Markov transition kernel M, let M times P be the marginal distribution obtained by running the Markov transition M from P. The learning gradient of the EBM at iteration T is the gradient of KL divergence between P data and P minus KL divergence between MQ and P. The MQ is the marginal distribution obtained by running the Markov transition M from the generator Q. In the traditional contracted divergence, P data takes the place of Q alpha in the second KL divergence term, meaning that the Langevin dynamics starts from the data distribution. As to the MCMC teaching of the generator, the learning gradient of the generator alpha is the gradient of KL divergence between m theta t times q alpha t and q alpha. Here, m theta times q alpha takes the place of p data as the data to train the generator model. The cooperative learning using MCMC teaching alternates between Markov transition from generator to EBM and projection from EBM to generator. These are the qualitative results obtained by the cooperative learning frameworks. Figures shown on the left-hand side are synthesized images generated by the cooperative learning algorithm. The latent space of the generator trained by MCMC teaching can also be useful for image inpainting and interpolation. Results are displayed on the right-hand side. The cooperative learning scheme can be extended to the conditional learning problem by jointly training a conditional deep energy-based model and a conditional generator model. Let X be the d-dimensional output signal of the target domain, and C be the input signal of the source domain. The goal of the conditional learning is to learn the conditional distribution P of X given C, which is the distribution of the target signal given the source signal. The two conditional models are trained jointly in a cooperative manner, where the conditional generator serves to initialize the sampling process of the conditional energy-based model, while the conditional energy-based model refines the initial synthesis by an iterative algorithm. The conditional EBM learns from the difference between the refined synthesis and the observed examples, while the conditional generator learns from the difference between the initial synthesis and the refined synthesis. The conditions can be one hot label or image. Here are some examples of applying the conditional cooperative learning framework. The applications include label-to-image generation, image-to-image translation, and silent object prediction. Now, I will introduce the cycle-consistent cooperative network for unsupervised image-to-image translation. Suppose we have two image collections from domains X and Y respectively. The examples of these two sets are unpaired. The cycle coop nets simultaneously learn and align two cooperative networks. Each contains an EBM and a generator for one direction of translation. We take the direction from Y to X as an example. The generator G from Y to X, which is parameterized by an encoder-decoder, maps examples from source domain Y to the target domain X, while the energy-based model P of X further refines the mapped result by Langevin dynamics, such that the revised results match to the examples in the target domain in terms of the statistical properties. The other pair accounts for the other direction. Two directions of mapping are aligned by enforcing mutual invertibility on the two generators. Here are some unsupervised image-to-image translation results by the cycle-consistent cooperative network. In the cooperative learning algorithm, we can learn the generator Q alpha of X by variational inference from the synthesized example X tilde generated by EBM. To retrieve the latent variables of X tilde, we bring in a tractable approximate inference network pi of z given X with parameters beta for inferring z from X tilde. The learning of inference model pi of z given X and the generator Q of X given z forms a VAE that treats X tilde as training examples. This is called variational MCMC teaching. That is, the VAE learns from the MCMC of the EBM. The VAE objective is a minimization of variational lower bound of the negative log likelihood of the synthesized examples X tilde. I compare different types of MCMC teaching in this figure. In the original MCMC teaching, the latent variable model will treat X tilde as training examples. Figure A shows a rigorous MCMC teaching with MCMC-based inference of Z given X. Figure B displays a fast version without inference. The variational MCMC teaching includes 3 models and adopts variational inference, which is different from the original MCMC teaching. I show image generation results by the cooperative network using variational MCMC teaching. The cooperative learning framework can also be applied to joint training of an EBM and normalizing flow model. The normalizing flow is a special generator whose log likelihood is tractable. To be specific, the transformation G in the normalizing flow needs to be invertible, and the log determinants of the Jacobians of the transformation can be explicitly obtained. Then under the change of variables, we can obtain the distribution of X. G is usually composed of a sequence of invertible transformations. In general, the density of X is intractable. However, with some smart design of the sequence of transformation, the exact log likelihood can be computed. Therefore, the parameters alpha can be estimated directly by maximum likelihood. Now, I introduce the coop flow algorithm that simultaneously trains an EBM and a normalizing flow model. At each learning iteration, the algorithm performs the following steps. In step 1, we first generate examples by the normalizing flow. The generative example is denoted by X hat. In step 2, we start from each X hat and run a Langevin dynamics or a short-run Langevin flow toward the EBM to obtain X tilde. In step 3, we then update the normalizing flow by treating X tilde as training data by maximum likelihood. In step 4, we update Langevin flow according to the learning gradient of the EBM by treating X tilde as synthesized data. Synthesized examples by the coop flow algorithm are displayed here. Each panel corresponds to a different training dataset. Here is a list of references of Part 3. Now I'm going to talk about latent space energy-based model in Part 4. Let X be the observed example and Z be the latent vector. We can learn energy-based model in the latent space of a generator model, so that the EBM serves as a prime model that stands on the top-down network of the generator model. The top-down generator G is parameterized by deep neural network with parameters beta. The prime distribution of Z is in the form of energy-based model, which is parameterized by MLP with parameters alpha. P alpha of Z is an exponential tilting of a non-informative Gaussian prime P0. With an informative energy-based prime distribution, the model can learn regularity and rules in latent space of the data. Moreover, MCMC in the latent space for both prime and posterior sampling is efficient and mixed well. Following empirical base, both the latent space EBM and the top-down network can be learned jointly by maximum likelihood. The model can be learned by maximum likelihood estimation. The marginal distribution can be obtained by integrating out the latent vector Z in the joint distribution of X and Z. The gradient of the log likelihood can be decomposed into 2 parts. The first part corresponds to the prime distribution alpha, while the second part corresponds to the generator beta. Both terms are expectations under the posterior distribution. which is dependent on the pry and the generator. The learning of the pry distribution is to match the pry and the aggregated posterior. And the learning of the generator is to reconstruct the data with the inferred latent vectors. MCMC is needed to approximate the expectation. We need to draw samples from the posterior distribution P of z given x and the energy-based pry distribution P of z by Langevin dynamics. Here are the Langevin update formula for sampling from the pry distribution and the posterior distribution. The energy term U in the pry distribution has a projective term which is due to the non-informative Gaussian distribution. The posterior distribution is proportional to the joint distribution, which involve both parameters of the pry and the generator. Sampling from the posterior distribution by Langevin dynamics is like a stochastic gradient descent algorithm that finds Z in the latent space to minimize the generator reconstruction and the energy function U in the pry distribution. I present the whole learning and sampling algorithm for the latent space energy-based model. In each learning iteration, we sample a batch of training data. For each training example, xi, we use Langevin dynamics to draw samples Z- from the energy-based pry distribution P alpha of Z and draw sample Z plus from the posterior distribution. We then compute the learning gradients by using the samples from the pry and the posterior distribution to update the pry distribution and the generator respectively. These are the synthesized examples by the latent space energy-based model. If the generator is defined as a conditional autoregressive model, which is parameterized by a recurrent network, the model can be used for representing sequential data. Z is an abstraction vector about the whole sequential data and controls the generation of sequential data at each time step. It can be applied to text data for text generation. Z will be the for vector about the whole sentence and control the generation of the sentence at each time step. It can also be applied to molecule SMILE sequence for molecule generation. The EBM pry captures chemical rules implicitly in the latent space. It can also be used for trajectory prediction as an inverse planning. The energy will serve as a cost function defined on the whole trajectory. The latent space energy-based model can be applied to conditional learning. For example, in the application of silent object prediction or binary image segmentation, we learn a distribution of silency map given an input image from the observed image silency pairs. The conditional model is similar to the unconditional one, except that the generator maps the image and the latent vector together into the silency space. The generator can be parameterized by a vision transformer architecture. Once the model is learned, the silency prediction of a given image is performed by sampling from the distribution conditioned on the input image. Some qualitative and quantitative results are displayed. This is the list of references of Part 4. This is the end of the tutorial. In this tutorial, I introduce the background of the energy-based models and present three categories of energy-based models. The first one is the data space EBM, which is a probability distribution directly defined on data domain. It is trained by matching the observed statistics and the synthesized statistics. The second one is the energy-based cooperative generative network, which trains an EBM and a generator simultaneously via MCMC teaching. The third one is the latent space EBM, which is built on top of the latent space of the top-down generator. For more information, about deep energy-based modeling, please check the references listed below. Thank you.